Hello everyone, and we are going to try this video thing again. I've actually just recorded two videos and both of them didn't work out, so that was very exciting. Today we are going to try and we're going to go over what we did in lab last time when you did the spring lab. And so just to review what our setup was, we have our stand over here. We have the spring hanging from the stand with that little hanger that you had on it with the needle that was attached to it, and the needle was obviously pointing to the ruler that was attached to the stand also. And so what you did in the experiment was you started off the hanger at some point, and then you put some masses, some objects of some mass on the hanger, and the spring stretched, and you read the new reading from the needle. So here's the new reading for the needle, here's the old reading for the needle. And so what I asked you to do was to come up with a mathematical relationship between the force that the spring exerts on the object and the displacement of the needle, or of the hanger, but the needle was there to help you read it. So first of all, we'll notice that our displacement is here, right? This is delta x. And as for the force of the spring on the object, how do we know what that is? Well, if we go ahead and start our Newton's second law equation, right, we know that we're only dealing with the y direction, so I'm just going to leave the x direction out of it. You know that's obviously 0. And so we've got ay equals sum of the forces in the y direction over m. And so we know that ay, once it's done stretching, ay is actually 0, right? So we know that 0 meters per second squared is equal to the sum of the forces in the y direction, which, I forgot to do this, if we draw a force diagram, here, we see that we've got the force of the spring on the object in the positive y direction, and we've got force earth on object in the negative y direction as per our axis. So when we put in the sum of the forces here, we see that the force of the spring on the object is in the positive direction, and the force of the earth on the object is in the negative direction, so that's negative, all over the mass of the object. And if we continue to solve, so we want to see what the force of the spring on the object is, well, we multiply both sides by m. The m cancels out, because 0 times m is 0, right? And so what we end up with is that 0 equals the force of the spring on the object plus negative force of the earth on the object, which means that we add force earth to both sides, and we see that the force of the spring on the object is equal to the force of the earth on the object. So in order to figure out what the force of the spring is on the object, all we had to do is calculate what the force of the earth on the object was. And so to do that, all you use is force spring on object, which equals force earth on object, which equals mg. Right? Where g, in this case, it should be 9.8. In this case, I'm going to use 10 just to make things easier. And so I asked you to take some data. And so let's say you took your data and you created a table for force spring on object and displacement, delta x. And let's say your data came out to be, I don't know, let's say the force of the spring on the object is 0.2, this is in newtons, this is in meters, 0.4, 0.6, 0.8, and 1.0. And let's say your delta x data was, let's say this needs to be in meters, so we're going to do it in centimeters. So let's say this one was 0.04, This one is 0.08, so that's 8 centimeters. This is, let's say, 0.12 centimeters, 0.16, and this is going to be 0.2 meters. So our ruler wasn't this big, but you get the idea. So if we look at the data here, we see that if you multiply 0.04 by 5, you get 0.2. If you multiply 0.08 by 5, you get 0.4. 0.12 times 5 is 0.6, and so on and so forth. So we see this pattern emerge, where if you multiply the displacement by 5, you end up with 0.2. And so this 5 that we came up with here, 5, 5, 5, 5, 5, is called the spring constant, K. And the units for the spring constant, if we multiply the displacement meters by 5, we need to get newtons. So the units for this is actually going to be newtons per meter, for all of these. And so K is what is known as a spring constant. So let's just reiterate what we have here. What we have is the force of the spring on the object is equal to K, which is the spring constant, times delta x, which is the displacement. But one thing that I would like to point out is that actually when we did our experiment, so we had, let me draw a force diagram here. So we've got force spring on object, and we've got force earth on object. And you'll see that when you have your spring, let's say with nothing on it, and then you have your spring with something on it, our displacement for this is actually here, in this direction. Right? It started here, this is x initial, and this is x final. And notice that this is downward, this delta x. But our force is upward. So as you stretch out the spring, if the force is exerted in the opposite direction that you're stretching. Similarly, if you were to squish a spring the other way around, then you would see that the force when you squish a spring is actually the opposite direction again. So let's say you had a spring that started like this, and then you squish it in this way. The displacement is this way, delta x. But the force that the spring exerts, the force that the spring would exert on you is this way. So the force that the spring exerts is always in the opposite direction of the delta x. So in order to account for this, we add in a negative here. And that accounts for the fact that the force that the spring exerts and the delta x are always going to be opposite. And so here is our new equation. Force spring on object equals negative k, which is the spring constant. This is in units of newtons per meter, times the displacement, which is given in units of meters, and of course the force of the spring on the object is given in newtons. And there you go. So I hope this was helpful. Tomorrow we're going to do practice problems involving this idea, and I hope you all do well. See you tomorrow, or next time, whenever it is. Bye.